Welcome everyone. In the previous sessions, we practiced using arrays and method integration. Today, we're diving deeper into object-oriented programming, OOP, with a hands-on application of classes, constructors, properties, and object arrays. These exercises will train you to design structured classes, handle data through encapsulation, and understand real-world abstractions using programming logic. Let's begin with the first problem. Our first problem, problem 1, focuses on designing and implementing an employee class. The objective, as you can see, is to create a robust and maintainable class by applying core OOP principles. This means we'll be thinking about how to structure the class, protect its data, create objects, and define its behaviors. Objective: safe employee class that adheres to good OOP principles, proper encapsulation using properties, multiple constructors for object flexibility, secure state modifying methods, correct implementation of equality and object representation. Step-by-step approach. Step 1. Define private fields and expose only controlled public properties. This structure enforces encapsulation. We hide internal data and access it through getters and setters. Notice the ID field is private, but its ID property has a simple public getter and setter that allows any value to be assigned directly. Compare this to name and salary, which use auto-implemented properties, a more common pattern, but still allowing direct assignment. A more robust design might involve validation in the setters, for example, ensuring an ID is positive or a name is not empty. Next, constructor redundancy. Constructors are special methods used to create objects. It's common to have multiple constructors to allow creating objects with different sets of initial data. However, if the logic for initializing the object is repeated in several constructors, it becomes hard to maintain. The problem points out the need for efficient constructor design, often achieved through constructor chaining, where one constructor calls another using the this keyword to avoid repeating initialization code. You can see that the lines setting this .id, this ditname, and this .salary are repeated in several constructors. This is the redundancy we need to fix using constructor chaining. Third, unsafe method behavior. Methods define what an object can do. If a method, like one designed to increment salary, allows input that leads to a nonsensical result, like a negative increment causing the salary to decrease, it's unsafe and breaks the expected behavior. See how it directly adds the inc value to this .salary without checking if inc is positive. This allows mp6.increment salary minus 500, which would incorrectly reduce the salary. We need to add validation to make methods robust. Finally, flawed equality logic. When you compare objects, you usually want to know if they represent the same real-world entity based on their data, value equality, not just if they are the exact same object instance in memory, reference equality. The default equality checks in C# are often based on reference. For an employee class, we typically consider two employees equal if they have the same ID, or perhaps the same ID and name. The problem requires implementing the correct value equality comparison. This main method demonstrates how the employee class is used. It creates several employee objects using different constructors, sets their properties, calls the increment salary method, and prints their details using toString. You can also see calls to get hashcode and equals. In the original problematic code shown earlier, running this main method would demonstrate the issues. For instance, calling equals on two separate objects with the same data would return false. After implementing the fixes we discussed, running this same main method would show the correct behavior, validating that the problems have been resolved and the OOP principles applied effectively. Moving on to problem 2, the motorway class. The goal here is to create a class that represents a motorway intended for use as extra documentation or with directions. This problem focuses on defining the characteristics of a motorway using properties and providing methods to retrieve information about it. The requirements for the motorway class are listed here. We need to include several pieces of data as properties, such as the highway's name, type, like road, street, boulevard, direction, surface type, number of lanes, whether it has a toll, and who maintains it. We also need methods to return specific combinations of this information: the full name plus toll status, and the full name plus the number of lanes. A standard two-string method is also required to display all data. The problem emphasizes including enough constructors for flexible instantiation, allowing objects to be created with varying amounts of initial information. It also mentions creating a class diagram, which is a great step in visualizing the class structure before coding. Here we see a potential solution code for the motorway class: fields and properties, encapsulation. We have private fields for each piece of data: name of motorway, type of motorway, direction, surface, number of lanes, toll, and who maintains. Constructors. There's a default constructor, and then several overloaded constructors taking different combinations of parameters: name, type, direction, name, type, direction, toll, etc. While constructor chaining isn't explicitly used with this, in this example as a strict fix for redundancy, the presence of multiple constructors demonstrates providing flexible ways to create motorway objects, a good design practice. Methods, abstraction. We have the required methods: return full name, return toll information, and return lane information, encapsulate specific logic for formatting and returning combinations of data. The user of the class doesn't need to know how the full name or toll information is assembled, they just call the method. This demonstrates abstraction, hiding complex implementation details behind simple method calls. The toString method provides a convenient way to get a formatted string representation of the entire object's state. Then, we have public properties for each of these fields. These properties have public get and set accessors, providing controlled access to the private data, illustrating encapsulation. The internal representation, private fields, is separated from the external interface, public properties. Although not shown in the code slides, a complete solution would also include the class diagram, visualizing the class structure, its properties and methods. And as mentioned in the problem, a second class, with a main method, would be used to create instances of the motorway class and call its methods and access its properties to test that everything works correctly.